Hello, everyone. My name is Amar Gowda. I'm a Principal Product Manager in Azure Confidential Computing. My area of focus is confidential containers and Kubernetes and cloud native. Today, we are here to talk about how do you achieve zero trust architecture goals and zero trust operator goals with Azure Kubernetes Service and an upcoming feature, confidential containers with Kata confidential container support. Let's delve in. So the primary principles of zero trust goals is verify explicitly, use the least privilege possible, and you always assume breach. These are the core principles of how you put a zero architecture to achieve your highest data privacy goals for your workloads. So the most important part here is the least privilege, right? So who's in your trust boundary, who's not? And you should always design your systems in a way that you put most of them out of the trust boundary, and the only thing is probably primarily your code and the hardware where it is running. So this is where confidential computing and confidential containers are very relevant. So let's expand a little bit on all the things that go into building a zero trust architecture. It's about minimizing the trust. Like I said, it's only the code you should trust and few other binaries that are needed. Access controls are super important. RBAC access controls through AKS, RBAC controls are very critical to achieving these goals. These are pretty well documented and curated the way we do it today and securing the remote access, right? For example, SSH, the agents that run inside of it, are you authorized? And the network policies around that are super critical. And the last part, or to the goals, is about visibility. How do you detect changes upfront? How do you block those changes upfront? So these are very critical components for achieving your goals. So confidential computing specifically does not solve the goals of your networking lockdown or storage lockdown, but specific to your execution environment, your CPU and in memory, right? That is very critical on how confidential containers adds a whole lot of value in this overall goals. So what are the product goals for confidential containers and what problems it is going to help solve you achieve the zero trust architecture? One, it's fully auditable and a transparent open source system, fully aligned with open source Kata confidential containers and Kata containers as defined by Confidential Consortium, CCC. We stick to the standards as much as possible and also upstream all of our code into the open source projects. This is critical in achieving the goals of transparency and confidentiality. And on top of this, it's also about the integrity of the data. That means the integrity of the code. You may have a ML model that needs to be encrypted and kept safe all the time. You can encrypt those models. And also, when the code is loaded in your environment, there are a set of attributes or environment variables that are critical in shaping what behavior of a container. Those need to be attestable as well. So those features are critical to the production goals. Immutability is another important feature. Once it's up and running, you want to make sure that security standard is always maintained and not changed, that you cannot detect it, right? This is where the immutability, it could be an important concept to overall to achieve your goals. And the last couple of things are all about attestation. You know, this is cool. This is a confidential computing environment, but you want to make sure, right? Trust but verify is equally important for some of the workloads where a client sending a personal identifier information needs to check that the server side of it receiving this information is authentic and it does meet your standards. And the last piece to it is the trust boundaries, right? Shielding as much as possible from all the operators. That includes cloud vendors, cloud operators, as well as your own administrators, which are critical in kind of achieving your goals of data privacy. So expanding on what sort of features are upcoming with confidential containers that can help you align your goals is we are building on top of AMD SCV SNP environment. This is the highest level of protection we could get with a full confidential VM type of a setup with ultra lightweight guest OS that runs containers. There are no Azure services in your trusted computing base. The only thing that is a fully open source software and your containers that you authorize to run, and that attaches also a policy on top of it. And the most important thing is we don't want to add overhead to the developers. So this environment is fully lift and shift supporting all Linux containers. That's our goal. If there are containers that are specifically prohibited, it could be because of the behavior and the type of actions they are doing that could kind of break beyond the confidentiality goals we have. And the most important thing to this is we've kept it so simple that it's just as simple as a line of change in your YAML file that you use for deploying your apps, right? A runtime class for Kata confidential containers is how it triggers this deployment. We'll look at a little bit detail the architecture on how this is put together. All right, so the technology stack looks, we are building on top of nested. Nested is a way how you could take a parent VM, take out the CPU and memory resources to a child VM and assign a confidentiality or a memory encryption parts to it with that runs as a CVSNP. So if you look at the left side of the picture here, you have pods, and every pod will get its own micro VM, which has its own memory encryption key, hardware root of trust from AMD itself, right? So all of this is fully measurable. You could see other components, what we call it as untrusted. You could see a little gray boxes below, which talk about the kata runtime as well as the hypervisor layers that kind of orchestrate all of this. This is all kind of very transparent to you when you deploy a agent node in AKS that has this capability using Azure Linux as a base OS, which is already super hardened and very tightly controlled on the component it loads. On the right side of the picture, you would see a breakdown of what all moving parts are in there. If you go deeper into the nested Kata guest VM, what you see here is basically your pod and a couple of agents that are helping you run those pods. It's very slim, lean, straightforward. There's nothing more than these components in there. So overall, this is how the technology stamp looked like. And we can get into looking at even a demo of how this works. And the demo focuses on two important things. One is the lift and shift capability. This is a use case where you have a streaming data. So the data we are trying to simulate here is a telecom operator or a telecom provider that has IMEI number, GPS coordinates of exact location of a cell phone on a zone. All of this is deemed as a PII information. This information can be used for matching with another data set, which is the scenario here. This is a Kafka stream using event hubs, which is our message bus where all this thing flows through. What we want to show here is an end-to-end from the producer, from the edge, all the way into cloud environment where this is processed, how you achieved your goals of data privacy with full end-to-end encryption and the ability to do lift and shift. Another most important component is Dapper. Dapper is an open source software that is very popular for abstracting away your bindings to event hubs. We've achieved the goal of running Dapper as is, unmodified in a confidential container environment. So I'll start the demo and I'll walk through how this works. So there's an IMEI number, which is encrypted using RSA on the edge. You have a message bus that is receiving the data, and you have confidential container environment receiving the data and processing it. What I'm showing here is a Kubernetes AKS deployment, which has Dapper, a plugin installed. That means it is running a control plane and some sidecar configurations. All of that is running in an untrusted side of it. So I'm doing a get ports to show you what is running out there. And I have a application that is built on top of Dapper. This is the app. This is straightforward. There is no confidential computing related programming model here. This is a plain vanilla .NET Core app. It's doing a crypt operation and trying to look for a decrypt where data matches to the data of interest. Here is your YAML file, and what you see here is as simple change as a runtime class kata CC isolation. That is what triggers this to run as a confidential container. So I applied this with kubectl, straightforward. You should see a pod, a confidential container pod running with 3 or 4 containers in there. So you can run more than one container in a single pod. Everything runs in a single utility VM, which is confidential AMD CVSNP protected. So I am right now getting pods to elaborate on those pods and show you the pods are up and running. And once they are up and running, I bring up a producer app that produces and simulates these messages. You have the consumer, which has started listening for the message bus so that they appear. When the messages appear, it starts processing them. So I kicked off the producer. Once the producer is done with producing all the messages, you will see the receiver side start receiving the messages right away. You could see the encrypted messages pumped into the message bus. That shows that the PII data is fully encrypted from the source. On the other side, where it's receiving, it does a decrypt operation. And the decrypt operation requires a key, and the key was securely delivered to this environment after attestation. And you will see there the data was matching because we was able to do a decrypt and try to do a match. I am here switching to the message bus or the event hubs and showing you that even in the message bus itself, you will see the data fully encrypted, right? So anybody who wants to sneak in, your own administrators cannot make sense of any of this PII data, right? So this is how we achieve the goals of end-to-end encryption. This information is showing you a plain text version of it, but there's no plain text. Everything is used using a RSA encryption. So this is the end of the demo, and this is data stream processing with Coco and AKS using Dapper. You could as well use this for your continuous ML training as well as ML inferencing. We also support encrypted container flow that can help you protect your ML models. To learn more about this product offering and how you can get engaged, go to aka.ms, Coco AKS. Thanks, everyone.